Well, hello from my office. I'm going to be testing this week, so my recordings will show me in the hotel room. So this is an assignment, or the slides Mr. Barnes did for us, Balancing Equations of Matter, Chapter 4. We'll be talking about chemical reactions and chemical equations the next 2 weeks, and then we'll have a chapter test. So I encourage you this week, Thursday, to do what you can to bring your assignments to 100%. The assignments then do both terms or both attempts on your quiz to get 100%. Use your graphic organizer. What we're going to try to do is try to explain as best we can. I'm going to be just a talking head this week. You're going to understand the difference between reactants and products, how to count for elements in a reaction, how to apply the law of conservation of matter, how to balance equations. A lot to do. Gets pretty frustrating, um, especially if you've never done this before, and it was for me when I first started. I can understand and label the reaction. I can practice counting atoms in a chemical equation. I can determine if a chemical equation is balanced, and I can learn the process of balancing equations. So lesson 1, I'm going to turn my screen off so that you guys can see this in bigger scope. All right, so it's a great idea to take notes. There are assignments in the week 16. So chemical reactions form new substances by breaking and creating chemical bonds. They change the way the atoms are arranged in their physical characteristics. An example, fireworks are a result of chemical reactions. So when you look at a chemical reaction, we sometimes use a chemical equation to show that. So there are reactants on one side and products on the other side. A chemical exchange that takes energy to break or create chemical bonds, or bond energy, holds elements together. Reactants, in the chemical equation, they are on the left side. Products, chemicals on the right side of the reaction. So what we talk about is in and out. The chemicals going in and the chemicals going out will be changed, or rearranged, but the chemicals here, let's take a look at this equation here. Hydrogen gas plus oxygen yields or creates H2O. So here we have some examples of bonds. You can get heat, object gets warmer, or an object gets colder. Those are examples of what happens when bonds break or combine. So 10 examples of chemistry in everyday life: vitamins, cleaners, hormones in your body, fire, paints, baking, synthetic fabrics, drugs, bug spray, cosmetics. So in a quick review, counting atoms, we talked a little bit about the coefficient and the subscripts. If in a parentheses, the subscript after the parentheses is multiplied by the chunk, everything in the parentheses, that multiplied by the coefficient. So if you can think about this, chromium chloride, CrCl3, and it has a coefficient of 2, which means it has 2 molecules of this. So I'm going to take 2 times 1. That'll give me 2 chromiums. And then 2 times 3, that'll give me 6 chlorines. Now, This is a little more complicated here, barium hydroxide. So you've got this parentheses over the OH. So that means that we are going to take that subscript 2. So remember, subscript means below writing or writing below. You take that 2 and you multiply the only that's in the parentheses. So H is 1 and oxygen is 1. So 2 times 1, 2 times 1. So we got oxygen 2 and barium 1. Now, this is the most complicated of some of the ones that I've seen. We have 3 molecules of calcium with chlorine and oxygen. So you've got calcium, 3 times 1. There's 1 calcium there. And then chlorine. So the 2 is going to multiply by the chlorine times 3. 3 times 2. You can see the arrows going there. That gives you 6 chlorines. And then 3 times 3 times 2 are 18 oxygens. Sometimes really hard to keep track of those. Visually, if we drew the molecule, it would be easier to see. So this is important. Counting atoms is very important because of the law of conservation of mass, stating that chemical reactions, atoms are not created or destroyed. Whatever is on the left side is on the right side. So that's what we get to this idea of balancing equations. Lavoisier, father of modern chemistry, in the 18th century, named oxygen and hydrogen, developed a metric system, experimented confirming that changing the state of matter, the total mass remains constant. So something that people thought at the time when you took water and froze it, that you got different, the atoms rearranged and became a different, it was a bonding type of thing. So that doesn't bond. So that's a physical property. Law of conservation of mass. So 2 gold atoms plus hydrogen sulfide, H2S. Okay, so this on the left-hand side is your reactant side. This is our starting. We start with this. You start here, right? And these chemicals react with one another. And in the reaction, sometime later, sometimes they take a long time to do, but sometime later, the reaction symbol, the arrow there, means yields, and it produces an Ag2S plus H2O. Oh, no, sorry, plus H2 leads to, okay, so if we take a look, this is what I said is this is yields or produces. So sometime later, right? And notice that there's silver. I think this is silver. Yeah, this is silver. Ag is silver, not Au is gold. So here we got silver here. We got silver here, silver there, sulfur here, hydrogen there. They just rearranged each other, rearranged. But we want to know if the left side equals the right. So let's take a look. So what I would do in this particular case, I'm sure he's got it on the next slide, but if I were to do this, I'll turn my pen on. Silver, so I've got Ag on this side, and I'm going to put an arrow or a line here for the Ag on the product side. There are 2 here, 2 there. Hydrogen, 2, 2. Sulfur, 1 and 1. Okay, so it is balanced. So again, the law of conservation of mass says the atoms going in, and so in is the same as going out, just rearranged. How does a balanced equation illustrate the law of conservation of mass? A balanced chemical equation shows that the same number of and kinds of atoms in both the reactants and products. Therefore, the total mass of all the atoms in the reactant is the same as the total mass in the atoms in the product. So let's take a quick look at the subscripts versus coefficients. Subscripts, the number showing how many atoms of the element are in the molecule. So in H2O, there's a subscript 2. There's the subscript. And that means below and writing. So that's the number. Okay. And the oxygen is 1. Now, again, I'll indicate a 1 here. I don't need to put it in, but that's how many atoms of oxygen there are. Coefficients, number showing how many molecules there are in a particular chemical. 3, total number of water molecules here. So this is the coefficient. I'm going to put a number in here. The coefficient tells you that you have 3. And I'll make a little molecule here of water, 3 of those, 3 H2Os. H, one more over here. All right, so 2, 4, 6 hydrogens, 6 total hydrogens. So 3 times 2 and 3 times 1 is 3 oxygens. All right, so let's count some atoms here real quickly. All right, so Na, C2H3O2. So Na, put a 1 there just to remind me there is 1. Na. Carbon is 2. Hydrogen, 3. And oxygen, 2. Again, subscript to the right and the lower right tells me it goes with this carbon, and because there are capital letters, I can tell they're all capital letters here. That tells me the difference between carbon and hydrogen and oxygen, and the small case A tells me that that's sodium. So remember, it's always a capital letter if it's by itself. If it's more than one letter, it's always a capital and a lowercase. Determine the number of atoms for each of these elements. Okay, so let's take a look at this. Magnesium, there's 1. Oxygen, there's 2. Magnesium on the product side. So this is reactant side. Here's the product side. Magnesium 1, oxygen 1. Okay, so notice magnesiums are balanced, but oxygens are not. There's too much on this side. So if we look at a balance for the oxygen, so I've got 2 oxygens on this side and 1 oxygen on that side. So this is just the oxygen. So I'm going to go over to this side, to the product side. And I'm going to put a coefficient of 2 there. I cannot put any subscript, no subscripts. Okay, no subscripts. So the only numbers I can put in here are the numbers in front here. Those are the coefficients, only coefficients. And those are the numbers that go in front of here. Now we're going to quickly erase a couple things here. All right, so I don't, well, maybe I can't. I'm just going to cross this out and cross this out because I put that 2 in here. So this is 2 magnesium and 2 oxygen. So cool, we're great here. We have 2 and 2, but we've kind of messed up the magnesium here. So what we're going to do is we're going to put a 2 there. Now we're perfect. We have 2, 2, 2, and 2. Put the 1 there if I want to. So 2, 1, 2. All right, so he did the exact same thing I did. Put a 2 in front of those. First he took a balance check. You need to increase the number of magnesiums we have on the reactant side. Adding coefficient of 2 will give us the number of atoms we need. We say we have an equation is balanced, and that's how we prove the law of conservation of mass. So let's try this. How many atoms are there in each molecule? Right. All right. So let me go back a little bit. Let's do this for a second. So we have 2 H's, 2 O's, 2 H's, 1 O. Okay, so because we can only do the coefficients, not the subscripts, I'm going to go to the side. Again, here I go. I'm going to go to the side with, okay, this is going to be out of balance on the oxygen. So the oxygen has 1, and on this side is 2. So it's heavy on this side. So this is going slanting down, right? So I'm going to go here, and I'm going to put this coefficient here on 2 for 2. So now I have 2 oxygens, but now I have 4 hydrogens. So that means I'm good on the oxygen. I'm going to put it at 1, but I'm going to change this to 2 because 2 times 2 is 4. Now I've got the equation balanced. Right? 2H2 plus O2 gives you 2H2O. Right? If all the coefficients can be reduced to lower number, they must be replaced by the greatest common factor. And Blake is the example of balanced. Right? So in this particular case, H2O brings you to, this is a decomposition reaction where we start with water and then we're breaking it into hydrogen and oxygen. If all the coefficients can be reduced to a lower number, they must be replaced by the greatest common factor. So this is a fake example. If I put 3 H2O here and 6 H2, that would give me 3. Those that balances out, but we're going to divide and get the right coefficients here. So this should be 2 to 2 to 1. 2, 2, and 1 is my lowest coefficients here. 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. So we divided by 3. I think yeah, okay, he didn't do this correctly, but it's all right. All right, so balance the following equation by adjusting the coefficients. Okay, so N2 plus H2 is NH3. So Here we have the reactants. So we have 2 nitrogens and 2 hydrogens, 1 nitrogen for the product, and 3 hydrogens here. All right, so we want to make this so that we end up with 2 nitrogens on the product side. So this is NH3 here. So we're going to add 1 more NH3. We'll get 2 of those. We're going to put 1 there, and then we're going to change this to 3 H2. So we've got 6 hydrogen molecules, 3 pairs of hydrogen molecules, 1 pair of nitrogen molecules to give us 2 NH3. All right, so that's where we're going to stop today. Thanks, ladies and gentlemen. I will make more recordings on the road in Ohio, Toledo. I will see you guys there if you're coming. All right, bye-bye.